You know, one thing looking back at my video list and kind of all the things that we went through so far, I'm realizing why teachers have issues following lesson plans. It's not, it's not that they want to run a run too far on stuff, but things just sprawl. Things just sprawl so much that it's almost let's get rid of this. Oh, things just sprawl so much. It's almost hard to reasonably state that there won't be overrunning, right? This in itself is supposed to be taking 3 days total. We're already on part three and we're 10 minutes into the video. All right, let's keep pushing forward. So we left off last, we went over weights and biases. We have a really good understanding of how they work now. Your inputs are essentially whatever patterns or that your filters find. And then by weighing each pattern, it'll connect each output a certain way. So, whatever we want to correlate spike length with safeness, if we create a higher weight to that spike length, then it matches to safe more accurately, right? The boundary decision boundary works better. So that's all
So
that's
it's helpful to
happening.
have a
And
side.
then biases allow it to slide up and down the y-axis. So now, and then hidden layers are essentially computational layers to where you take your inputs and you apply it to hidden layers to then use that calculation into the output layer. Um, this allows for better, more robust, I guess you could say, calculations.
And they can have as many nodes as we like, and we could even have multiple nodes, layers,
So we looked at
and
the
let's see
code.
what. So
So now here we are with activation functions. All right.
let's go back to our design and zoom in on a single node. In a loose analogy to biological neural networks, we can think of this node as a neuron and the weighted input over here as some sort of stimulus. If the stimulus is sufficient,
Okay. So your node, right, is a neuron. And your weighted input, which can come from anything, this weighted input is technically the output of the classify function. The weighted input, right, is whatever we want to weigh, the spike size, the spot size, the shape of the fruit, etc., gets placed inside of this neuron,
stimulating, that should cause the
which
neuron to
is
fire, which in our model could mean outputting a value of 1, whereas if the stimulus is small, the neuron wouldn't fire, so we'd just be outputting 0.
okay.
I'll refer to this output as the activation value, so
So the activation value is the value that comes after inputting the weighted input into a node.
we just need to write a little function that takes in the weighted input and
Okay. So we're creating a function that ingests the weighted input
computes that activation value. Something
and then return weighted input
like
greater than
this.
0.
And let's
So I actually, if I'm being honest, I don't know what this means. And I've seen it enough times to now need to understand it. So I'm assuming it's question mark 1 or 0, right? Somehow, if weighted input is greater than 0, uh, if it is greater than do output 1, if it's not greater than 0, something like that, right? Uh, what was this? Control Shift T? Yeah. Okay. Uh, we were saying duh 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 does what? It was a semicolon. Question mark 1. There is no extra bit to it. Unclear question would be crazy. Evaluate condition. So is the weighted output greater than 0? If it's true, if it's false. Okay. So we were right. It's just a one line. So just a one liner. Essentially, it's just a one liner for if statements, in my opinion. and y equals if x is greater than 3, then y is 1, or it's 0 if it's not greater than 3. Okay. So if the weighted input is greater than 0, return 1. If it's not greater than 0, return 0.
Let's quickly visualize that with a graph. So the x-axis here shows the weighted input, and the y-axis shows the corresponding activation value. Using an activation function like this
So you're saying this is the activation function, and then this is the weighted input. And what you're saying is, oh, I see. No, no, no. So the weighted input is here, is this x axis here. Because what you're saying is, as the moment x is greater than 0, just by a little bit, output 1. And it stays 1 for everything else. If it's before and it's less than 0, right? So this right here could be all the way down here, but it gets normalized to 0.
should allow us to have more complex decision boundaries. Before we can try it out,
And that's how we get the bend on
though,
side of the
we'll need to quickly
decision
jump into the
boundary
layer
from here, right?
script, and instead of outputting the weighted inputs over here,
Instead of outputting the weighted inputs on the calculate outputs, which this is taking in the weights and biases that he's using the
let's pass
sliders
them
for.
through the activation function.
So you have the weighted input, which is what you're receiving from your previous layer, and then you pass it through the activation
And
function,
then output those
and then you're passing either 0 or 1 through it
activation values
because of
instead.
that,
So returning
right? So your activations,
to the joyful process of
okay,
randomly tweaking sliders until something happens, we can at last see that we're able to actually make simple shapes with the decision boundary. And of course, increasing the size of the network now would allow us to make increasingly
I will say, while this is helpful in a way, I feel like it's also hurtful because this is a very simplistic 2D representation of how it really works, and it almost simplifies it to a fault, is how I feel. Um, Now that I understood the concept that we're only able to do this because there are two values, and that is the key point behind all of this, there's only two values, it's not very replicative of how the real world is going to work, right?
fancy shapes.
But
But this tiny
now that I
network is
understand,
already
I
sufficient
can
to
see what he's
correctly
going for.
classify the made-up data we have at the moment.
So these weights, right, these biases, these weights, all of this would be automatic. It's easy with two, right? You have two, they're pretty relatively plotted nicely, but if this was all different types of sprawled out, what would be happening is as we keep going through runs, the AI itself would be altering the patterns and how everything is shaped out so that um, it could fit. Like if this was blue, this was blue, this was blue, this was blue, it would have to curve and twirl in the perfect way to match everything that can probably only be done by automatic AI.
By the way, you might have noticed that the
Or it would take us so long messing with these sliders that it would just
biases
be
no longer simply
pointless.
shift the whole boundary up or down like they did before. Instead, they're just a way of easily shifting the value that goes into the activation function. So, thinking of our biological
And yes, it's no longer just the y-axis because all these different weights are going through the activation functions, which create these angles. Now the biases are essentially just as abstract as the weights.
analogy, it would be like a threshold that the stimulus needs to exceed in order for a particular neuron to fire. Now, one thing I don't
And each neuron firing, in my opinion, is the change to the decision
like about our
boundary.
current setup is how abruptly and dramatically the output can change in response to just a tiny tweak to some of the
This to me, though, to me, that's because of the activation function that we're using. Because our activation function is either 1 or 0 and it's binary, every single small change doesn't change anything until the weight matches beyond or below 0. And only then will the decision boundary change. If we had a different function, which allowed the weights to move a bit or the changes to be a bit more gradual instead of just a binary one and zero, you should be able to see in that case more fluidity and moving around stuff.
these sliders. So let's
Sliders.
go back to our choice of activation function and maybe replace it with
Okay, okay. Let's these are these might be important eventually. So I'm okay. Activation functions. Step function. I'm not even gonna do it. I'm not even, step function. um uh binary bigger or smaller, 0 normalized to 1 or 0. Right, and you guys understand how we get this. It's either gonna be 1 or 0 depending on if it's bigger than 1 or 0.
something like this instead.
So this is a we actually taught I believe this is a log function with 1 over something. Reciprocal function, log or x. It would have to be log. Exponential, you have an exponent. Log functions are like this, I believe.
Which simply smooths things out.
Which then turns that into this because now, as you saw for y, if x is 0, you're getting zero point 0.5 instead of 1 or 0. Right? You're not. It's not an if statement. You're actually calculating.
This is called a sigmoid function, by the way, and it's just one of many different functions that people have experimented with for neural networks.
Sigmoid
Here's a few others, just as a matter of
comma
interest.
curve.
Anyway, let's go with this one for now and see how that affects things.
There's more, like,
Neural
but
network.
I mean,
With this once again,
yeah.
and we're now able to make nice smooth boundaries. And more importantly, making small changes to any of the sliders will no longer result in a drastic change to the output. Anyway, as fun as it is trying endlessly to train this network by hand, the goal of course is for the computer to do it all by itself.
Uh,
And
which is exactly what we said.
for that to work, it's going to need a way to measure how well it's doing. One approach would be to simply count the number of known data points that are being classified correctly. But the trouble with that approach is that often making a small adjustment to one of the sliders won't actually change that number, meaning it's impossible for the computer to know if that adjustment was beneficial or not.
Makes sense.
So we should try find a more precise way of measuring progress. Let's think about the outputs of our network again.
Which we know. And this is a sign of us as a whole getting better with this because we haven't had to stop for a minute and kind of rehash things, right? We 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 could speak on what's happening, right? These are the hidden layers. These are your inputs. This is the outputs of whether being safe or poisonous. We can understand the concept at hand without needing to go look everything up.
Which are now being squished to
As I say that, we're gonna have to look something up soon, probably, but you get what I mean.
somewhere between 0 and 1 by our sigmoid activation function.
Oh, so you still stay within 0 or 1, no matter what, but it's there's so much levity within the two sides.
So if we give the network the inputs of a fruit that's safe to eat,
Okay, so you're inputting something of food that's safe, which says, let's say, has small spike size, small spot
we'd hope to
size,
see a 1 at the first output and a
and 0 makes
0 at the
sense.
second output,
And then if it was dangerous, it would be 0 for safe, and then 1 for dangerous.
representing total confidence that it's safe. And for a poisonous fruit, that should be the other way around.
But what if you get 1 and like zero point
So
0.7?
since we know what the outputs should be for our training data, I've added a little function to the layer script called the nodecast, which
So we're going to start talking about costs now. Functions that allow for mapping better. that's a really bad explanation. So let's actually dig a little more into activation functions, which came from so long. I don't even remember where we started this whole activation function route from. But this was from forever ago that this got brought up of a node, right? So the node can be, say, poisonous. It's a function that calculates the output of the node based on its individual inputs and their weights. So the middle layer boundary that we had, right? Let's see if it's still up.
which takes training data.
So this second layer is going to have an activation function of itself, which again, we are creating the layer class, so we can specify the activation layer within this class. Um, and it'll calculate the output of the node. So it'll calculate this output based on its individual inputs, which are this input, and their weights, which will have a specific weight for this connection, have a specific weight for this connection. This and this will also have specific weights for these connections. These connections will have specific weights. And then it does a calculation here, which then provides what you output there. And then this does the same thing, takes ingest all these inputs, calculates activation function, normalizes it to whatever. Okay.
I've added a little use is
So
a single node.
let's look at the function. Double node cost, double output activation, and then double expected output. So this to me can only live on the output node. Double error equals output activation minus expected output. And then you multiply it. You square the error for some reason. But what's happening is you're saying output activation is going to be whatever that calculation happens to be minus the expected output, which is coming from probably, I don't know what,
Along with the
honestly.
value we want it
Oh,
to be.
there you have it.
All it does is calculate the difference between the two and square the result, just to make it positive and I guess to emphasize large differences as being much more urgent to correct than small
Uh-huh.
differences. Then in the neural network script, I've added a function simply called cost.
So costs and it ingest a data point uh, object. And then you're saying an array of outputs equals calculate outputs, data point dot inputs, which is coming from this parameter here. So it has all the inputs. So we're saying, you know, let's crack open Paint real quick. I actually did buy something to do this with, like an actual pad. I just had to hook it up, and I'll be using that next session. So we have this, we have that, we have this, we have that. Right. And this is the layer we're working on. And this layer is going to have data point dot inputs. And then the layer output layer equals layer layers dot length minus one. So whatever. Oh, it just only focuses on the very last uh poisonous or safe double cost. You started with zero for node out, and then you just calculate the cost of each output that's expect versus what's expected. Okay. This
Which
is a
takes in
loss function. Okay. And we've seen loss functions so many
a single
times.
data point, such as one of our fruit, and runs its inputs through the network to get the output values.
So it runs through the entirety of the network, right? Because it's working with every single layer. Um, and it gets the value. This is essentially the training part, right?
Using those,
You're saying you raise the cost if the difference between what's expected and what's actually output
it then
is
adds
too
up
high,
the individual
is high,
costs of
if
all of
there
the
is a
nodes in the
difference.
output layer to get an overall cost telling us how badly the network is doing for the given data point.
Okay.
We're most interested though in how the network is doing across all our data points. So here's another version of the cost function which takes in multiple
So this takes an array Um, this takes in an array. Double total cost for each data point, and data, which is this here. Total cost plus equals all the. Okay, so you loop through every single point, and then
multiple data points this time, and
it
just
should
adds up
return
each
the
of their
mean, I
costs
believe.
and returns the average.
The average. Average is the mean.
So you can see that value at the bottom of the screen, and the goal of the network is now simply to find values for its 17 weights and biases here, which result in the smallest average cost. For the tiny network we have here, we
Ah,
could probably even get away with a brute force trial and error
you just keep.
approach, but our networks are going to get a lot bigger as we tackle trickier problems, so we should definitely try to find a better solution. Let's
I
simplify
see.
things by thinking first about this little example function.
One thing I like about this guy is whether it's performance or on purpose, he smiles when he talks, and it's nice to listen to.
Where, similar to the task of finding the weights and
So we have a function return. This is just, I assume, just a function.
biases that minimize the cost function, we want the computer to find the input value that results in the smallest output,
Uh-huh.
or at least some reasonable alternative. And
Uh-huh.
of course, we'd like it to do this in as few steps as possible, not just calling the function millions of times.
I have seen this before. Yes, gradient descent. Okay. I'll say a couple, maybe last year, I started trying to watch the Harvard uh, AI essentially courses, and they touched on this. And this was how they introduced gradient descent by finding the smallest point, yada yada, but they didn't explain weights, biases, or anything. So now looking at this, I understand
Until it finds
what's
a good
going on with
answer.
the cost
Now, our solution
and the
is going
loss
to rely
functions.
on calculating the slope of the function. So let's try writing some code to visualize it.
All right, so draw slope. So
We can approximate the slope very easily by first defining some tiny value, which I'll just call h, and then calculating how the output of the function changes in response to this tiny positive nudge to the input. The steepness of
so this is just raw math. I'm not gonna. All right. Yes, I have a feeling this will come eventually in handy, but this isn't what we're here for.
the slope will just be this change to the output divided by the change to the input that caused it. So,
Okay.
as I said, this is just an approximation because we're technically calculating the slope between 2 points on the graph, but the smaller we make h, the closer our approximation will be to what the true slope would be precisely at the given input value.
Go.
Anyway, we can then visualize the slope with a bit of code like this.
Cool, cool, cool.
Let's see how that looks. So the slope value is
That's
pretty
dope.
intuitive. We can see, for example, that it's negative over here because the function is decreasing as the input increases, but it's getting closer to zero as things level out.
That is
And once
so
the function
cool.
starts increasing faster and faster, we can see the slope value increases as well to reflect that.
Mhm.
Now, for a function like this one,
Okay,
we
hold
can
on.
directly envision
That's so cool. All right, let's learn the math behind it. All right, so he he created this function. That's just a function, right? This in itself, we could assume are data points, right? This is just a
on
function for the sake of
calculating the
having a
slope of
function.
the function. So let's try writing some code to visualize
So
it. We can approximate the slope very easily
of x, right? So one, two, three, whatever x value.
by first defining some tiny value, which
So you define a tiny value,
I'll
okay?
just call h, and then calculating how the output of the
How the output of the function,
function
this,
changes in response to this tiny positive nudge to the input.
so function x plus h, right? Minus function x. I see. So the change of this function if I add zero point zero 0.01 to it. So we have this function. This function doesn't do anything. I mean, wait a second. Yes. So this function is going to calculate all of this. This could be, let's just say this is x plus 1, right? Or y equals mx plus b. So let's say it's mx plus b, right? So it's just creating M's 1, right? B's nothing, whatever, right? So then we say, so let's find the delta output, which is going to be the difference between the now bigger number of y equals m x plus 0.1 minus y equals mx. Right.
The steepness of the slope will just be this change to the output divided by the change to the input that caused
So then you say the output here, whatever it's calculated to be, divided by
it.
the small one will give you the
So,
slope.
as I said,
I guess this is just,
this
math.
is just an
The
approximation
math.
because we're
The math
technically
mathing, right?
calculating the slope between 2 points on the graph, but the smaller we make h, the closer our approximation. Anyway,
So then we are saying vector slope direction, new vector 2, 1, slope dot normalize, vector point equals, this is doing stuff. Cool.
let's see how that looks. A bit of code like this.
Point vector 2, yeah, this is
It
not,
was pretty intuitive. The
I'll
input
be honest, I don't know.
increases.
I don't think it's really
Now, for a
relevant,
function
but
which would be super efficient, actually do some maths to directly calculate the points where the slope is 0, which would be super efficient and wonderful. But unfortunately, that maths just isn't viable when it comes to our actual neural network. Instead, we're going to be relying on a technique called gradient descent.
here
And
we
the
go.
idea here is that we'll pick a random starting value and
Uh-huh.
then just slide down the slope into the valley.
Okay.
Here's some code for doing exactly that. It initializes the input to a random value.
Okay. So gradient descent. This is by far going to be this by far is going to be one of the most important things we come across simply because of how much I've seen this. So let's get into it. Sliding function to find slope 0.
And
So you input value equals random value, right? So this could be a random value generator function, whatever the case may be. Let's say it's 2.
then in this learn function,
So then you have a learn function, okay? So you get the delta output, which is the input value of this random number. You find the slope of the situation. If its slope is going down, then you just keep following down because you're bound to hit 0 eventually. And when you do hit 0, then from there, okay, now we keep going. I guess, hold on.
it approximates the slope like we did a moment ago. And
So value tells us whether the output of the function is increasing or decreasing at the current input value. Yes. Input value minus equals slope times learn rate. Where's learn rate? Here. I guess how quickly we want to do jumps on the
then simply subtracts the
input.
slope value from the input value. And this learn rate parameter here just allows us some control over how much the input changes with each iteration.
Uh-huh.
Let's try it out. So I'll give us a random starting value, and then I'll just go press this learn button a bunch of times to repeatedly run the gradient descent algorithm.
So it'll go down until it hits the
And we can see
0.
it's very slowly making its way down the slope.
And
Then we'll restart this.
but if you go too fast, it might jump the slope, and then now it's going up with by missing
And try
the
again with
0,
a much higher learn
where
rate.
cost is 0, which is what we want. See, now it misses.
But now it's clearly trying to learn too quickly because it's just bouncing around all over the place and not making any kind of consistent progress.
Well, that's
So
insane.
we
This is beautiful.
need to try strike some sort of balance with the learn rate, and if we manage to find a good value for our specific problem, we can see it's able to learn pretty efficiently.
There you go.
Of course, there's no guarantee that we'll fall into this optimal solution known as the global minimum. We could very easily fall into a local minimum instead. But
Uh-huh.
this process tends to give good results in practice, and there are all sorts of things we could experiment with in the future to try and improve it. So to get a better picture of how this will apply to our actual network, let's pretend that the network has just two weights. And these will start out with random
And these will be weights for your two inputs.
values, so let's imagine them over here, for example. Now, if we want to know how good these weights are, we could run all our data through the network to calculate the average cost.
which we could imagine like a straight line going through here, and this is just piping all the data through.
And let's represent that as a height in the
Let's go. Let's go. Are we understanding these concepts or are we understanding these concepts?
third dimension. We can then imagine the average cost that would result from any configuration of weights as a kind of landscape like this.
This is how they described it. Let me actually bring that up for you.
Hey, my name is Ben. Today I'm going to explain linear classification. Make sure to like and
Yeah.
subscribe if the video.
Let's see if we could actually just look at these side by side. Harvard AI. Which one was it? Was it that? Maybe? Was it Stanford? I don't think it was Stanford.
All right.
Uh,
Okay, less than zero.
nah, this wasn't it. I want to say it was Harvard. I'm like pretty sure it was Harvard. Uh, this, I know for a fact they went over gradient descent. It's not that big of a deal. Ace was this guy. It was Stanford. It was.
Morning, and we'll make some of the math a little bit simpler. So
Here
cos
we
theta
are.
1 theta.
Same exact concept, is it not? Same exact concept, but now, you jump straight into things and you just jump with this. I mean, what are you looking at, right? But now with the understanding behind it, you don't want these. These are bad. These are wrong. This is good. You want to try to find these right here. And it's doing a good job at showing like the x and the y-axis, but also the depth inside of that.
Now, in the previous example,
So we're saying, so let's say here, we have two weights here, right? This is spike length, and then this is spot size. So as the spike length grows and the spot size is a little bit bigger, right? A little bit bigger than zero, this is your safe zone. If we're looking for, let's say, safe, right? When the spike length is whatever this value would be considered, right? If we're starting from zero technically to whatever infinity, if the spike length is 2, then you have, and then you have no spot, right? The spot is the spot, there is, let's just say this is directly on the x-axis, then this is considered safe, right? That's how you handle your gradient descent. And they were picturing it as like a ball kind of rolling down. Yes, the ball might roll over here when this is deeper, but either way, it rolls and it will find the smaller areas.
we approximated the slope by looking at how a tiny change to the input variable affected the output of the function.
Yep.
And we could do the same thing here. We'd look at how a tiny change to the first weight affects the cost, as well as how a tiny change to the second weight affects the cost. And these two together tell us the slope, or gradient rather, of the cost function with respect to the weights.
Makes sense.
So if we subtract the current gradient from the weights, again using the learn rate to control things a bit, that'll cause the weights to move downhill. And so with each iteration of gradient descent, we can imagine our weights rolling further down the slopes of the cost function,
Just like a ball.
before finally settling into one of the values. Now, obviously, in our actual network, we'll have loads of weights and biases affecting the cost, so this is all happening in more dimensions than we can hope to imagine, but the idea
That's
remains
beautiful.
exactly the same. Alright, I'm going to go ahead and implement all the stuff we've been talking about, and I'll see you then.
So now we're programming gradient descent, signing.
So, over in the layer script, I've added these two arrays for holding the cost gradients with respect to the weights and biases.
Okay.
Then we have this new apply gradients function, which takes in the learn rate, and it loops over all the
So we are adding cost gradient WB, weights and biases. Okay. And then update the weights and biases based on the cost gradient. public void apply gradient double learn rate, which is going to handle if you want to speed it up for int node out. Okay, for the out. So we're talking the output for this. Let's say this is the middle layer, right? Layer two.
the weights and biases and just subtracts the corresponding value
So biases of the node out. So bias of, let's say, safe here is subtracted by the cost gradient B, which is up here,
from
which,
the gradient from
and it's kind of weird looking at it programmatically because we are physically inputting these. So you think about it like bias is automatic towards the node that we're looking at. And then the cost gradient B is already automatic, but we can multiply it towards learn rate.
each of them.
And then this weight is automatic for the matrix of whatever connection. So let's say we have that A connection connecting to safe. The A connection of this of layer two, right? The A connection of layer two connecting to safe. This right here is going to have its weight. Um, so we're saying this weight of, let's say it's 12 normally, equals now the cost gradient of that weight, which is a different array of itself, times learn weight.
I've also added a function for giving random starting values to all of the weights, which looks like
And you're initializing
this.
random weights inside of the matrix for node in and
Now,
out.
in the neural network
Wonderful.
script, we have this new learn function, which takes in all our training data, and it starts off by using that to calculate the current cost value.
Okay.
Then, for each weight in the network, it makes a tiny nudge to that weight to measure how much that causes the cost to change.
Yep.
And it resets the weight after doing that, just to not throw off the calculations for the rest of the weights.
Makes sense.
Then it calculates this value here, telling us essentially how sensitive the cost is to the current weight, and stores that in the gradient array. This here is just the same process for the biases, and at the end of all of this, the gradients are applied on all the layers.
So,
So
show us what it
as
looked
long
like.
as the learn rate isn't set too high, this process should cause the overall cost of the network to decrease each time we run it. So let's return to our potentially poisonous fruit to see if it actually works. It has quickly found this linear
That's
boundary, which does an
awesome.
okay job of separating safe from
But
poisonous.
it still needs to keep
and
going
the cost
down.
is still going down, even though not much seems to be happening. So let's give it a little bit longer to contemplate matters.
And this is where GPUs come in and
at
handle.
last,
Oh
it's
my
managed to
god.
perfectly classify the training data. So our neural network is learning, which is exciting. The problem we have now, though, is that it's excruciatingly slow. This is mainly because we're having to run the cost function for every single weight and bias parameter.
Mhm.
And remember, the cost function needs to feed all of the data it's given through the entire network. So one thing we could try
I
is
see.
simply to give it less data. When we give it all the data we have, we can see the cost goes down nice and steadily as it lands.
Mhm.
But if we had hundreds of thousands of training samples, it would take a really long time just to complete a single learning iteration.
Which is basically what we're gonna have to
Instead-
do at the end of the day with. So like this would work fine with what I have for the AI for determining between cornerbacks and receivers. But once we start getting into, I mean, good breaks and dropping your weight properly, sticking outside the body, stuff like that, I mean, you're getting into like
if we just
hundreds of thousands. We're gonna need an
give
easier
it a
way to do
tiny
it.
portion of the data each time, we can complete learning iterations much faster. This does make the
Ah,
learning process noisy because we can imagine our cost landscape will look a bit different for each mini batch, so they won't all agree exactly on which way downhill is. But it does speed things up immensely, and the noisiness can apparently even be beneficial in a number of ways, for example in helping to escape the dreaded saddle point, which are regions like this, which can slow the learning process down dramatically.
makes sense. It's a dip, but do I go left, right? Which is, I see.
So this mini batch technique is a big improvement, but by itself it's not enough. If we want to scale our network up to say tens of thousands of weights, which is actually still very tiny, then that would mean running each data point through the network tens of thousands of times as well. And so
Oh,
our
right, because it's this data point, and you have to deal with the weights of every single connection. But then you have to realize that this connection now, depending on the change of this weight, is still gonna have to then connect to all of these, which then influences all of this. So then, and that's just one point. You have to run through the entire iteration of everything it touches over again.
Networks could take pretty much forever to learn anything interesting. Happily for us, there is another
Jeez.
way to calculate these gradients.
Which is, dang, that's crazy. Okay. Which I'm really happy about, right? I'm really happy we're seeing this. I love the pattern right there. That's great. I'm really happy we're seeing this because we understand the limitations now, right? Why it's slow. For this, let's say this is fruit shape, fruit size, spike length, spot size, fruit color, right? And we want to focus on the fruit color. So we pass the fruit color to 12 different layers inside, right? And each connection to these 12 layers will have different weights. Now, let's say I want to update the weight on layer one. There needs to be a change here. Everything else in this entire ecosystem stays the same. But if I change this one line connecting to layer one to node one, you still have to recalculate everything else afterwards because this connects to here, but then this also connects there. So even if it was just these two, this final connection on this node, this activation function is going to be different because the weight here is different. So you still have to then calculate this node, which gets to here. But if this node is different on this activation calculation, you have to still calculate everything on this one node. It still has to do everything else because the activation itself, activation function will be completely different because this one prior node is different. And then that sprawls between every single node on the next layer and the next layer. I mean, it's insane the amount of time it would take to learn properly.
Where for each iteration, we'll only have to run
And this is just a handful of this is a handful of things, right?
our data points through the network once.
Imagine it being, receiver forward lean, foot separation, number, size, like height, weight, uh, footwear, accessories, helmet, right? You have all these different patterns, 64 of these that it shows normally, right? That's the second convolution layers. Normally you're at 64, you drop the height and weight by half, and you're at 64 inputs. Well, no, you're in 64 layers. How many inputs it may have extracted from that, I don't think is guaranteed. It might not extract anything, but let's just say it extracts one pattern through each layer. So you have 64 patterns now connected to, let's say, if we're doing 5 to 12, we can say 64 to 128. So 128 of these connected to maybe then another 64, which connects to two outputs. I mean, if this is tens of thousands, that might be millions. You know what I'm saying? So it's interesting.
And all it's going to
Very
cost us
interesting. Calculus. All right.
is a bit of
So we are approaching some calculus, which I'm okay with. Um, but I do think this requires some. This should be in a data in itself, right? We'll go with calculus, chain rule, partial derivatives, and then probably stop around digit recognition, back propagation. Yeah, we're gonna do this chunk tomorrow. We actually, considering our pattern, we did a lot today. We did 12 minutes today, and we understood the whole 12 minutes of it. We were able to break down the programming factors, the programmatic language that was being used a lot better, understanding weight, the cost gradients. I mean, we're zooming through this now, and I mean that's how it works, right? As you learn things, progress starts slow, slow, slow until you rise exponentially. And I believe we're probably somewhere around here right now. We're starting to feel the progress get a little easier. So that's good. It's somewhat short today, but it's really more about what we learn rather than the time spent learning. I do hope that y'all learned something. I know I did. And as I sign out, I will let y'all
And these two together tell
watch
us the
this
slope, or
beautiful,
gradient rather, of the cost
beautiful
function
backdrop.
with respect to the weights.
And I'll see y'all tomorrow.
So if we source the weights, but the idea remains exactly the same.